Hello, everyone. My name is Zhuyun Zhu. I am glad to have this opportunity to present our work, RGB Event Fusion for Moving Object Detection in Autonomous Driving. During this presentation, I will be covering four main parts: the motivation behind our research, the method we used, the results we obtained, and the DSEC mode dataset. To start, let us discuss the motivation. In reviewing other existing RGB event fusion methods, it has become evident that most of them utilize a single range event as input with a single directional fusion design. Unfortunately, this approach neglects the rich temporal cues and does not thoroughly explore the cross-modal relationship between the two data sources. We pose the question to ourselves: how can we enhance the performance of the RGB event fusion method? In response, we developed a network that benefits from multi-scale temporal events to better handle object motion. In addition, we incorporated a bidirectional fusion design to more effectively model multimodal features and attentively form the shared representation. In summary, to fully leverage the advantages of event cameras, we sought to study the movements with temporally multi-scale event inputs. To better merge the characteristics of RGB events, we proposed a bidirectional calibration and fusion approach. The specifics of our methodology will be elaborated on in the upcoming section, and our results will follow. Regarding the methodology employed, we developed an architecture called ReNet, which stands for RGB Event Fusion Network. The primary innovations of our model are the event-based temporal multi-scale aggregation, ETMA, and the attentive fusion with bidirectional calibration, BDC modules. The BDC module carefully merges cross-modal information using techniques such as cross-channel attention, cross-spatial attention, and concatenation convolution to effectively calibrate and fuse the characteristics of RGB and events. We also propose a module called ETMA, the abbreviation of Event-Based Temporal Multi-Scale Aggregation. According to our observations, as the event camera is an asynchronous sensor, to generate a frame of events, the choice of interval is very important and subtle. If the interval is relatively short, the frame contains fewer points, but the outlines of the objects are rather exact. If the interval is relatively long, the frame contains more points, but the outlines of the objects are vaguer. To fully benefit from the temporal cues and improve feature modeling, we developed the ETMA module. This module uses a small window for processing short interval frames and a larger window for longer intervals. Its primary aim is to optimize the utilization of temporal cues. Here is an overview of our architecture. As input, we take RGB frames and event frames. The ETMA is applied in the event stream, and the RGB stream is rather conventional. In the encoder, we perform the fusion of RGB and events for each layer, meaning that the BDC is used every time the two modalities merge. The encoded results are then passed on to the decoder. Finally, we'll compare the detection estimation with the ground truth to calculate the loss. Now I will present our results to you. Firstly, let's discuss the quantitative results. Here is a comparison chart with SOTA fusion alternatives. We compare the performance of our model with different types of alternative models. For example, with a basic setting, we also tested the performance of RGB-only, event-only, early fusion, and late fusion. We also tested the self-attention modules and the cross-attention modules, which come from recent top conferences, such as CVPR, ICCV, ECCV, ICRA. The criteria are frame MAP and video MAP. Our network had the best performance for all criteria. Here is a qualitative comparison and visualize our results. We have selected several models from the table for this comparison. The ground truths are marked in green. The baseline results using only RGB are marked in yellow. and the results obtained with our ReNet RGB event fusion network are marked in red. Now let us take a look at some demo sequences from our DSEC mode dataset. Here are 3 demo sequences under different illumination conditions. If you are interested in more details about our work, please visit our GitHub project page at github.com/zzy-zhou/renet. Thank you for your attention.